Welcome to JVM Roundabout number 20. Those of you who are regulars, you'll know who I am. My name's Ben. I work for a company called TRG. Anyone joining us for the first time, welcome. So we're talking about robotics tonight. So it's actually something we've never covered at the JVM Roundabout before. So we're actually really excited about it. As I say before every meetup, we do have social media channels. We're trying to get the meetup more support and more following. So if you can hashtag JVM Roundabout, if you do put anything online, you can see our Twitter feed in the corner. So just to make an introduction to the two speakers, we've got Matthew Cornford, Head of Product, handling robotics at Ocado Technology, and Chamara Jayala, Senior Robotics Engineer at Moley Robotics. We're looking forward to hearing from both of you. So yeah, I will let Matthew start, get the event going. Thanks a lot.
Thanks a lot, Ben. Good evening, everyone. As Ben said, I'm Matthew Cornford. I'm a head of product at Ocado Technology, looking after an area we call handling robotics. And today I'm going to talk to you about how we use Java at Ocado Technology to orchestrate robot swarms. So if you don't know who we are at Ocado, then we are a technology company who are trying to transform online grocery through cutting-edge technology and serial innovation. In the UK, we have an online grocery retail business, Ocado.com, but in recent years, we've been moving to power grocery businesses all around the world with our kind of advanced robotics and leading a grocery e-commerce solution. So we've been using Java at Ocado Technology for quite a few years now, at least 10 as long as I can remember. And we use it across the whole of what we call the Ocado Smart Platform. This is an end-to-end grocery e-commerce platform for global grocery retailers to take their businesses online. And so we offer everything from web shop, mobile apps, supply chain systems, advanced automated warehouses, on-the-road driver and delivery software, all for our kind of partner businesses around the world, like I say, to deliver the best service to consumers and get their groceries online. My experience comes from working in our automated robotics space, and that's what I'm going to talk to you today about, how we use Java there. So to give you a flavor of our solution and what our robotics looks like, I've got a short video which I want to show you. And so this is the robotic solution that I have the luxury and pleasure to work with every day. And we believe this is the most automated warehouse in the world. Everything you can see in this video is developed in-house at Ocado Technology. And I'm going to talk to you a couple of examples here of how we use Java. One about how we use Java in the development of the onboard robotic control software. And one about how we use Java in our air traffic control like overarching software, which is controlling this whole swarm of robots. So our system can support many thousands of robots roaming at any one time, communicating with all those many thousand robots in real time, issuing them instructions in real time. So we have some really genuinely interesting and complicated challenges in the software we're developing. So I've got three main sections I'm going to talk to today. I'm going to start with actually why Java. Java is not always necessarily the most obvious language to be using in this space. I'm going to talk about why we use Java. I'm going to talk about a few of the optimizations we use when developing our kind of air traffic control style control system. And then finally, I'm going to use an example of how we actually test the embedded robotic software with using Java as well. So why do we use Java at all? Well, I've got this slide in because anyone who kind of if I get into more details about this software, people always ask us, why are you not using software like C, C++, more recently, why are you not using Rust? And these are valid questions about why we might not be using those languages instead of Java. But obviously it's a trade-off for us, and what we're trading off is the difference between performance and how quickly our developers can actually develop. We are working in an agile environment. We are working in a very complex environment. And so having our developers be able to work fast is really important for us. And we feel that Java gives us the best balance between a performance system and one that allows our developers to go fast. Some other reasons about why we use Java. I mean, it's an evolving platform. That has been highlighted even more recently with the 6 monthly releases of Java in the last few years. You know, the platform is rapidly evolving. Every 6 months, new features are getting into the hands of developers. The Java and the JVM is generally just getting better, more performant. And so we're able to leverage that evolving platform to our benefit. And I've got an example later about where we've done that. And lastly, actually, by using Java, it gives us access to a global talent pool. Java is always listed in whatever ranking you look at as one of the top programming languages in the world, which means for a growing business like ours, by using Java means we can get access to a lot of great talent across the world. So when we think about all these things, rather than just necessarily the technical details or the technical aspects of a language, this often leads us to continue to choose Java as our language of choice, both, like I say, in the automated robotics space, but also across our whole platform. So if I move on to talking about some of the optimizations we make in our control system software, I'm going to focus on two today. I've only got about 20 minutes. I'm going to give you an example from some event scheduling optimizations that we've done and some garbage collection optimizations that we've done in our control system. So event scheduling, like I sort of tried to describe when I showed the video, we have a piece of software which we liken to an air traffic control system. This is sitting over the entire grid, and it's commanding, like I say, multiple thousands of robots all at once, communicating with each of them 10 times a second, and then so processing tens of, if not hundreds of thousands of events every second, and having to issue commands back to those robots in real time to keep them moving. And so we have quite a need for quite a performant event scheduler. It needs to allow us to schedule events for very specific times in the future. We need to ensure that any individual event we schedule in the future will actually be run at the time we want it to be run. It can't be delayed for any arbitrary reason. And we also can't allow those events to back up, because what happens if events back up or if events are delayed, then the system basically stops. We need to keep those robots continually working to keep the throughput of the system very high. So if you're an old school developer, you might kind of turn to a class like timer in Java. Hopefully, kind of that is well too old that no one turns to that anymore. Another kind of obvious choice in the Java kind of JVM libraries is a scheduled thread pool executor. This definitely meets the need, our first requirement of being able to schedule events for a particular time in the future. But actually, as I'll describe now, it doesn't actually meet some of the other some of the other requirements. When you go and schedule an event, kind of, you don't really necessarily, unless you read the documentation, know what's going to happen when that event comes to be scheduled. But if you dive into the source code of this class, what you'll find is that actually, depending on how you set up this class, when a new event is going to be scheduled, going to be executed, it might decide actually to create a new thread. Now that's quite bad for us, because a thread can take quite a bit of time to be created. And so that sort of breaks our requirement of any single event kind of not being arbitrarily delayed. If we have an event and the executor just decides it wants to create a thread, well, that will delay our event being scheduled and kind of may mean a loss in performance from our system. What you also see if you look into this class is that it has an unbounded queue of events. So again, if things start running a bit slow, then that unbounded queue will just continue to grow and grow and grow, and events will back up. And again, that's not something we want to happen. We need our events to be processed on time and not being backed up. So what did we do to address these problems when we can't find a solution within the standard Java toolkit? Well, we wrote our own. So we talked about why that class doesn't meet those requirements. And what we created is what's known as a busy loop. And so this is some sort of very simplified code of what our event schedule looks like and what the busy loop looks like. So I'll start from the top. We have a queue. That is a queue of events. And then we have a while true loop. So this is a loop which is going to continue forever. And basically it's continually looking at whether there is an event to run, if it's the right time to run that event, and if it is, then it will run it. So this is great, but it has some pros and cons. I mean, if you Google busy loop on the internet, actually a lot of sites and a lot of advice will be not to use it, and in most cases that's true. But in our case, with our quite tight requirements, it meant we were actually able to get our latency for events being processed from about 5 milliseconds down to effectively 0. Like I said, because that time of when that loop going round and round and round, as soon as that event is ready to process, we will run it. We also saw that actually because of that, we could get 3 times higher throughput of events through our busy loop than we could in our system using a scheduled thread pool executor. So this was great for us, and I say it's a prime example of some optimization we had to perform in such a kind of strict environment and with strict requirements. What are some of the disadvantages of actually doing this? Well, you use 100% of a single CPU or a single thread. So, you have to be willing to dedicate a whole CPU to that loop. This is one of the reasons why you get a lot of advice not to use it, because there's a lot of wasted CPU time where events aren't being processed and you are just spinning through this loop. But for us, that was a cost we were willing to pay. And an interesting side effect is that actually by running 100% CPU constantly for a prolonged period of time, you can actually reduce the clock speed over time, which was an interesting aside. So that's something we monitor and look at as well. So that's one area where we have kind of performed some optimization in our system, where the standard sort of Java libraries didn't provide us a solution for what we needed. Another area where we spend a lot of our focus in this system is garbage collection. Again, kind of as I said before, we really don't want events to be paused or delayed in running. And garbage collection, unfortunately, is a primary source of pauses in our application. And so if we don't get our garbage collection under control, well, it can wreak havoc in our control system, and the whole kind of the whole robotic system you saw can come to a halt. And so we spend a lot of time profiling our system and making sure garbage collection isn't having too much of an impact. So I've got some examples here of some things we've done to reduce the impact of garbage collection. These aren't things I would necessarily recommending as standard advice, but these are the sorts of things that when you're really having to optimize quite finely your system that we've done. And so if you think garbage collection is all about object creation and freeing those objects once you finish with them, a lot of these tips basically come down to using less objects or stop using objects at all. So we don't use optionals in APIs which are heavily used. Optional is an unnecessary extra object, and any APIs that are being hit at higher frequency, well, we don't use them there. That it removes an object and hence removes some pressure on the garbage collector. We use for loops instead of streams API, again, only in those places where your profiling shows kind of really hot spots in your application runtime. The streams API is great for readability, and I would recommend it 99% of times. But kind of from when you profile and test, if you find examples where kind of the, say, hotspots and the garbage collectors being hit hard, then you can reduce some of that object creation by moving to for loops. Similar, let's say these are all tips on a similar theme, using array-backed data structures instead of kind of object-based data structures like hash set or linked list. And an interesting we found is actually avoiding boxing and unboxing, especially in places where you might not expect it. So log lines in particular can be a nasty culprit for that. But like I said, these are not things I would recommend you do just litter throughout your code. These are tips that we've done, like I say, from extensive profiling and that we do in the right places. Some other tips when dealing with garbage collection, enable your garbage collection logs by default. They're cheap to collect, but very handy after the fact. And understand the different garbage collectors that Java offers. I'm going to talk about 2 different ones in a minute, and you'll see why it's important to understand the difference. And yeah, don't just take the latest and greatest garbage collector, because actually what we found in our profiling is sometimes the older garbage collectors can be better depending on the style of application you're developing. So I want to talk about 2 of the more modern garbage collectors now briefly, G1GC and ZGC. G1GC was released, if I remember rightly, in Java 7 and became default in Java 8 or 9. And ZGC was experimental from Java 11, and I think it's just been made non-experimental in Java 15. And why these are of interest to us is that they promise low pause times. So G1GC, you can control how long the pause is, which for us in a real-time system is really important. Being able to have that control of setting or indicating the maximum time we want our application to pause is powerful for us. And obviously everything comes with a trade-off. So that trade-off in control comes in by kind of higher use of CPU by the garbage collector as it's doing work while your application is running. ZGC, on the other hand, promises even lower pause times than G1GC can, kind of down to 10 milliseconds. So for us, that was extremely exciting when it first came out to try it. And we did some tests to compare these 2 garbage collectors. And this is, again, just highlights why we use Java, because what we see here is how we were able to gain quite a significant benefit in our system by us being on an evolving platform. We didn't have to do any work to develop these garbage collectors. We got them for free, but we were able to make the kind of utilize the hard work that's been put in by the Java and JVM developers. And so what this is basically saying is this the percentile of pause times. Lines higher up the graph are bad and lines lower down the graph are good, and basically just showing that a large percentage of the ZGC pause times were a lot shorter than that of G1GC, which was great for us. This is the same data presented in an equivalent graph. This is showing how much of runtime in a test is being taken by the application. So G1GC, the application was running for 98.94% of the time. So that means for 1.06% of the time, the garbage collector was running and our application was not. And when we looked at ZGC, that went all the way up to our application running for 99.82% of the time. So that's something like a 5 times reduction in pause times, which is incredible for us. So for the last few minutes, I want to talk about actually a slightly different example where we use Java. And this is testing the embedded software which runs on the robots themselves. So the problem we're trying to solve here is our embedded software is written in C and C++. And if you've ever developed in those languages, historically, they've been quite costly and slow to test. Tooling got better these days, but I'm not sure if it's quite getting up to the level it is in Java. We promote agile development and continuous delivery across a whole of Ocado Technology. We want our C and C++ developers to kind of have that same mindset and be able to practice those same practices as our Java developers. And like I said, we're always trying to optimize for the speed of our developers. Being able to have them run their tests quickly and get fast feedback is really important when you're developing. And yeah, like I said, we want all our developers to have access to the same sorts of tools. So what this meant was that what we're doing is we are testing our C and C++ embedded code using Java. we have an integrated test environment where the three languages run together. We're using Java to kind of mock out hardware APIs. We're also using Java to write the actual tests. And then everything is packaged up and run in the JVM. So that means the C and C++ code is being kind of called, loaded in the JVM and run within the JVM. So kind of an interesting snippet of how you do this. If you've ever done this before, you might know that any header file that you have in your C or C++ code, you need to translate to a class file for the integration to work. When you have one class file, well, that's quite easy for a developer to do and keep that maintained, or even write the class file respective to the header file. You have several header files, then obviously you need to replicate that into several class files. Again, quite easy for a developer to maintain or to write a handful of classes and duplicate that. But what do you do in the case of our system, where we are testing a big library of embedded software, which has hundreds, if not thousands, of header files? We really want our developers maintaining and writing the equivalent number of class files. Hopefully, I've stressed so far that we are always focusing on the speed of our development, and so the answer is no. We don't want developers doing this. It turns out, if you're interested, there are some really cool open source tools out there that can automate a lot of this boilerplate code for you. So a tool called JNA and BridgeJ are two open source libraries which you can go and Google, which kind of help us to kind of link the Java and C++ code together and free our developers from having to think about that, and actually let them think about writing tests and testing their software. So I just want to finish this section by talking about some of the challenges you get when you integrate Java and C into the same runtime. Well, garbage collection is limited to your Java code. The GC can't look into your C or C++ code and start freeing memory. That's not how it works. And so you have to make sure your C code doesn't blow up, doesn't leak any memory. Yeah, so that's one challenge. You have to kind of think very carefully about how your C code is going to run. C code can actually pass back bad objects, so objects which are like untype safe. So maybe it might pass back an array of the wrong length. If you've ever programmed in C or C++, or C in particular, you don't get that luxury of knowing you have to maintain the length of your arrays by hand. And so it's quite legitimate for your C code to easily kind of pass back a bad object and it just crashed the JVM altogether. You don't get a nice exception, you just get a nasty kind of stack trace and the JVM blows up. Testing asserts in C code is quite tricky. Again, we obviously in our test code, we want our code to test edge cases as well. That sometimes means actively wanting to hit asserts. Again, you don't get nice exceptions when you hit an assert normally just blows up your C code and in turn blows up your JVM. And so we had to work around introducing some kind of intermediary layers to catch those asserts so that we can carry on running our JVM and test all those edge cases. And one of the last challenges we've had was around JVM startup time. So when you're running hundreds or thousands of tests, depending on what unit test framework you're using, sometimes that means the JVM starting up many, many times and actually loading a DLL, loading some C code, and even just kind of loading the JVM itself can be costly and lead to quite long running tests. So we became very sensitive to tuning our tests and our setup to make sure that JVM start time was as small as possible. Again, because we're interested in kind of that feedback loop for our developers to make sure they can get their test run as quickly as possible and their speed of development is quick. So to summarize, we love Java at Ocado Technology. We use it across the whole platform, and like I say, it provides us with many benefits, as of one example showing, kind of ever increasing performance as well that we could sort of get from free from the JVM. We write our highly performant low latent control systems for our robotic warehouses is in Java. And like I say, we also use Java in a more maybe unusual scenario to test our embedded C software. So that was a bit of a whistle-stop tour. Thank you for listening. I hope you found that interesting. And yeah, if you're interested in looking for a job, we are hiring. Thank you very much.
Thank you. Can you hear me?
Yep.
Yeah, Matt, thank you. That was great. Appreciate it.
You're welcome.
So there are a few questions. I'll start with someone who just identifies as C. So hi Matt. How do you prioritize what the team needs to be working on at any given time?
Yeah. So that's not, I suppose, not really a Java related question. At Ocado, we have a large army, I suppose, of product managers, and we use product management and that craft and expertise to help us do prioritization. So we kind of follow an empowered autonomous team model. Every engineering team will have an engineering team leader and a respective product manager. And it is between the team leader and the product manager to understand their product, understand what need their product serves and what needs it needs to serve in the future, and hence make sure the right work is being prioritized at the right time. So yeah, like I said, I'm a product manager myself, so I spent a large part of my career as an engineer and moved over to product management recently, because actually prioritization and making sure we work on the right stuff is really important. I think really important to me and really important in general.
Cool, thank you. So next question is from Corinro. He actually, I know him quite well. We've met a few times. Yeah. So can you see that, or do you need me to?
I can see that. Yeah, I can read that. Yes. So we don't run Java on the robots themselves. Like I say, it's in the embedded C software which runs on the robots themselves. We use Java in our development environment to help test that software. The air traffic control software I was talking about earlier, that is a server process that runs on a server in the data center. And that will talk over actually a proprietary wireless protocol that we developed in Ocado Technology based on kind of 4G technology. That's how it communicates with each robot kind of 10 times a second. So like I say, in our warehouses where there are over 1,000 robots, that's kind of over 10,000 messages a second being sent out to all the robots by that server process.
Great. He's also caveated that by saying great talk as well in the comment section.
Thank you very much.
This is the last question we've got, as you can see from Channa.
Yeah. So that's a really good question. I have a much longer version of this talk where I talk about how we do use simulation very heavily in Ocado Technology to test both our embedded software and also our air traffic control light control system. So simulation is a key part of how we develop at Ocado Technology. Unfortunately, kind of 20 minutes didn't really give me the time to talk about that much. But yeah, we always want to test in the cheapest way possible, right? So kind of following the testing pyramid, and simulation allows us to get much better test coverage in the office before we start to put our code and test onto real robots and test it against real hardware. You know, you want to be absolutely sure, even in our lab, we want to be sure that the software we kind of deploy onto real hardware isn't going to break it. All right. We have different phases of testing, obviously unit testing, component testing, scenario testing, kind of full system simulation testing. And, you know, we try and do as much as possible in the office before we actually then go and run real robots in one of our test labs. And then before we get on to deploying into our actual warehouses, running controlling real hardware.
Thank you. Yeah, just seeing if there's any more. No, that's it. So yeah, thank you very much. Thanks,
no,
Ben.
Pleasure. Thank you for having me, Ben. Kind of enjoy talking this evening. Cheers.
Just before you go, is there any, like, if anyone thinks of anything they want to ask you or connect with you, is there any way they can?
Yeah, you can find me on Twitter at Bofalot, BOFALOT. Find me on LinkedIn, just Matthew Cornford on LinkedIn. Yeah, so happy to connect on Twitter or LinkedIn.
Quite often people just think of things they didn't ask at the time, so that's great.
No, more than happy to kind of connect with people and answer questions that way.
Great. Thanks very much. Okay. So for everyone watching, we'll switch this round quickly and get Shamara set up for the next talk. As mentioned, he's a senior robotics engineer at Moley Robotics. He's actually not a specialist within the JVM space, but because it was quite a unique subject tonight, I thought Shamara was obviously very relevant to talk to you guys. So take it away, and obviously any questions, just put it in the comments again. Okay.
Hi, good evening, everybody. So I'm Kamar Jailat from Moley Robotics. So at Moley, we are building a fully autonomous robotic kitchen. So the idea is we mimic the motions from chefs and try to cook any recipe as much as a human would. And this is our robot, what we have at the moment. Yeah, so the idea is to cook anything coming from a recipe. Yeah, so as you can see from here, and also in a lot of robotic applications, robotic arms are very, very crucial. So today, what I'm gonna be focusing on is how to build robotic applications with robotic arms. So robotic arms are basically a chain of mechanical links which are controlled by joints, which are actuated by the motors. So the question is, you have a robot which can move, and it has a degrees of freedom of the movement depending on the number of joints that you have. So the question is how you can do something useful or some task using this robotic arm. So today I'm gonna introduce you to two toolkits and go through a little bit of the code to show you how we can pick up object and place it on a different table, basically. So let's go to the requirements for this. So the first thing is we need to model our robot, and then the environment, of course. And then we need to sense the environment itself. And then we need to, since it's a pick and place, we need to create the motions for the robot without any collisions in the environment. And then after, so you can go from somewhere to the other place with the robot, and then you need to create the feasible trajectories that can be run on the actual hardware of the robot, depending on the velocities, acceleration, and the torque of the motors, basically. So to go a little bit deeper into these requirements, so how would you model your robot? So the main thing is you would get the robot configuration normally as a URDF file in the robotic community from the manufacturer of the robot, which defines the relationship between the joints of your robot. This gives you the geometrical representation of your robot, and also from the manufacturer you will get the dynamic configuration of the robots, like the velocities, the accelerations, the motor torque that it can go with. So the URDF itself will come as XML, and given this, you can basically model your robot. So given that you have these parameters, let's get this two-arm robot as an example here. So this is my robot. It has two joints to move, and given these joint angles, I can find the geometrically where my end effector is, which is this XY here. We call this forward kinematics in robotics. So given you know length of your links and the joint angles, you can find where your end effector of the robot is. And then the other question is, okay, I have my robot somewhere and I want to put it somewhere else in a different pose. Let's say X1, Y1. And then the inverse kinematics is to find the joint angles here to put your robot to that place. So given we can find this mathematical definition for the forward kinematics and the inverse kinematics, I can put my robot anywhere in the space, basically, where it can reach, obviously. So given that, the next thing is I have to move my robot from one place to the other, which means to go from here to there, I need to find continuous configurations of the robot without colliding as well with the environment. So this is called motion planning in the literature, and there are different algorithms to do this. And finding the correct algorithm for your application, of course, depends on the kind of application you do, as well as the environment you work in, as well as the capabilities of your robot. So given that you have a configuration, okay, I want to move from here to here, the robot, and I know how it would go from which joint angles to which joint angles. But still you need to tell the robot how fast, with which acceleration, with which motor torques that it should go. We call this trajectory generation, so time parameterize your motion plan, and that gives you a robot configuration with respect to the time. So it's a function, the function with respect to the time, basically. So given this, I have my robotic motion as a function of the time. I can send these commands to the robot controller, the position, velocity, acceleration, or torque, depending on the API or the interface the hardware provides, and you can start to move your robot. So this is kind of the very, very small introduction to the requirements that we need to have to develop such an application. And because of the complexity and everything, it's as developers, it's very important to find a robust toolkit to do this. So robotic operating system, in short, ROS, is one such framework. So it provides you with the tools to build your robotic application as a computational graph of nodes. And this node can communicate to each other using ROS messages. And you can see here a small example. So we have the ROS master, which registers all the nodes in your application, and it allows you to it allows the nodes to know each other and communicate between each other using ROS services, topics, and actions. And the language-wise, ROS supports C++ and Python at the moment, and there is experiment version of Java. So the good thing about ROS nodes, so if as a Java developer, you develop a camera controller, for example, and I, as a C++ developer, develop some backend in the robot controller, let's say. But we can still communicate between each other using ROS messages, even though we are in different languages. So it's language agnostic, which is a very good thing in the development. So the next thing is a MoveIt. MoveIt is a toolkit which is built on ROS, which provides complex algorithms for kinematics, motion planning, trajectory planning, perception, and all these kind of necessary algorithms for robotic operations. So when as MoveIt itself is a ROS node, you can communicate with MoveIt using ROS commands or ROS messages, and can interact with your robot and also use the capabilities from MoveIt to get, let's say, kinematics or the collisions of your environment. And then we have RViz, which is a 3D, which is a toolkit used to visualize the robot model and your environment. As well, RViz allows you to develop UI plugins that you can load in the RViz and start to interact with the robot itself. So these are basically the main toolkits that we will be using to build the robotic application. And these toolkits are used by a lot of industry and a lot of research community, and there's a big support from a lot of people, and it's evolving really, really fast. So in our application, as we told, we have this move group where I'll be communicating with to get the robotic functionalities and use the robotic algorithms. And then we have the world model where we will update our environment with. And then I have the camera controller here, which is simulated right now, where I would get the current environment object poses, for example. And then the RVS node will be the UI interface to us to communicate with other nodes. And then let's say that I get a robotic configuration from some manufacturer, which defines me how my robot geometrically looks like, and also the other parameters like velocity, acceleration, limits. I can go to the Movie Setup Assistant and load my robot there and start to configure this particular package in the way I want to control my robot, as well as which kind of algorithms and which kind of plugins you want to use with Move It in your application. So we load the robot here. It's easy. You load it, and you can also define the self-collision, which are allowed for the robot to happen. And then you can go ahead, and because your robot is somewhere and you want to link it to your environment, which is your world coordinate system, let's say, and you can define it here. And then with these names, you can also access it in your code. And then as you can see here, our robot has a gripper here, and as well this actual robot arm here. So I can define different groups here. So I define here from the base to the last joint here. So this is one move group that we use for all our planning and stuff. And then I can also use my gripper separately and configure it in the Move It, and it will use as a separate group. Yeah. And as well, so this is done now. And I go ahead, let's say my robot is somewhere, and I want to actually, after doing something, I want to put my robot in a default pose always. And I can do these sort of things here. I can move my robot and I can tell, okay, this is my default pose. And I can save that, and I can use this in my code with the same names, which are done here. So you do all of these configurations here. And then I can export this package, which is a ROS package, to my file system that can be used to access all the robot related robot related capabilities. Yeah. So the next thing is, given that we have our move group package to access the robotic functionality, now let's go ahead and see how we can create actual robot application. So the first thing is to use Catkin and create our workspace. So I go here and I create my folder, pick and place project, make a source folder there where all my code will lie, and then do a Catkin init and Catkin build, and you have your Catkin workspace. So you have your Catkin workspace. In our application, we had 4 nodes. So I will go to show how one node is created, which is the pick and place node. So inside the source folder, I create a Catkin package with the pick and place, which is the name of my package, and the dependencies. And then the folder structure is like this, and you can start to build inside this package now. So as I said before, we want to communicate with the nodes using the ROS messages, and creating ROS messages are very easy. So I define my messages in the message definition file here. So I have, as the request, I have 3 strings here: object ID, and from which surface to which surface I want to move my object from, and then the return response from the operation, whether it's successful or unsuccessful. And then in CMake list file, we can use this generate macro message to generate a macro to generate the messages. And this will be a pre-built process which will generate the source file I need to use in my project, depending on your language, of course. Yeah. So given that, the next thing, I will go ahead to show you a little bit of code, how to use ROS to develop your node. So in ROS, node handle is the main thing which will handle your communication with other nodes. So you need to have a node handle in the place where you initialize all your servers and clients to talk with other nodes. So here, for example, I have this pick server which advertise one service pick and place object, and then my callback to my callback function, which will do the actual work when somebody asks me to do pick and place the object, which comes from UI in this case. And then I have a bunch of other clients and one service to update the camera, etc. So as you can see, it's really easy to implement the communication and your channels to communicate with different nodes using ROS. And then the next thing is I have my nodes and I can communicate with my nodes, and then I can put my code, what the actual work I want to do. The next thing is how can I communicate with my move group and my move group and get the robot functionally to work with. So I'll go to the next slide to do that. So the move group actually provide you with different interfaces to access the functionality from move group, and internally they will handle the messages and responses and everything. So here, as I told you before, I use one move group interface, which is for my robotic arm, and then I want to use the pick functionality from move group. So I create a move with grasp message and tell the grasp pause where I want to grasp my object from, and other variables that are necessary to be set there, like where I'm coming to grasp my object and how far I'm going to grasp it, etc., etc. And then you just need to ask the move group to pick the object, and internally inside the move group, it will do all the collision checking, inverse kinematics, and motion planning for you, depending on the configuration that you put in the Move It Assistant. And the work will be done there actually. And then I have this pick and place node now, and to run this one, I can initialize my ROS environment in my main function and start my pick and place executor. And ROS also provides you with launch files to launch your nodes, which looks like this. And you can also have very complex launch files where you can launch different nodes all together and pass the necessary arguments inside that. Yeah, so this is basically how you can easily build a robotic application using ROS. So I will quickly go ahead and show you what I just did here. So I will load my application, and as you can see here, so my environment is loaded. It's just 2 boxes and 1 object here, and my robot is there. And this all is handled by move group, the whole visualization and everything. And then I can open up my panel, which is my UI, this pick and place UI, and I have it here. And I'm going to simulate my camera. Okay, it updated the object, and I'm going to ask it to pick this one. So it's going to plan everything and go ahead and pick it and do the placement itself. Yeah, and done. And I have the other button as well, which should do it in the other direction. So I did it in the other orientation. I'll go ahead and do the placing. So this is basically just a very, very small example how to use the Move It. But I can show you how we are using that one in our project. So this is our application where we have all the models loaded and use the Move It and the ROS to build our robotic application. So this I'm running with the simulator now. So we're gonna press some buttons here of the kitchen stove, and all this planning and everything is done with the capabilities from Move It. Obviously, we develop our own algorithms when it's necessary, but there are a lot of support from ROS and Move It to do these kind of operations. So that's kind of it from me. So I just wanted to introduce you guys these tools that are there And the good thing is you don't need an hardware to try these out. You can use the simulators provided by Move It itself and go ahead and try them. So yeah, so thank you. That's it from me actually. And I also put some resources that if you wanna go ahead and check this out. Yeah, thank you.
Okay, yeah. Can you hear me? Yeah.
Yep.
Thanks, Jamara.
Yeah,
just
sure.
having a look at. Okay. Well, obviously, Matt, you've actually got a question yourself. I'm happy to read it. Do the two arms collaborate or work independently?
They collaborate actually. So for example, if I want to do a steering of the pastime cooking, let's say, so they will collaborate. I'll take this one, for example, and steer with the other one, or some other operations where I want to put spices together, or while I'm steering, I want to put spices together. Yeah, so they collaborate actually. Yeah, they do collaborate.
It's pretty cool.
Oh, thanks.
Yeah. So Shanna has a question. This is really interesting. What are the system requirements to run this software? You can see that question now.
Systems requirements to run this software. Yeah. So mainly as we need a powerful PC obviously to run our algorithms, and we do all the main algorithms in C and C++ at the moment. So this is one thing. We need the GPU as well to run some algorithms and visualizations as well. And the other thing is to communicate with the actual hardware from the robot. We use a PLC, and the PLC is the safe file system that we use to communicate with the PLC and run the robot itself from the PLC. So we send the commands there, and we have basically these two systems as in terms of the main hardware requirements in terms of the computers, let's say PCs.
Okay. You can again, yeah. Questions there.
Geodogarize the whole simulation environment or run it on bare metal. You can do that. At the moment, we are still kind of bringing the system together. So at the moment, we run it in our main PC basically, and communicate directly to our PLC. But you can have it as a Docker as well, the whole simulation environment, and try the algorithms as well. We can give it to somebody with the Docker version. Yeah.
Just check, give it and see if any other questions come through. At the moment, that's the last question. So yeah, that looks like the last question. So yeah, I mean, guys, firstly, two speakers, Matt and Jamara, thank you for your time.
Sure.
And your
Thank you, Ben.
So obviously, if anyone thinks of questions for you guys, we obviously do have the JVM Roundabout group. So on Meetup, anyone wants to put anything in that, if they think of anything tomorrow, I will communicate with the guys. Yeah, look, thanks everyone for attending. Hopefully soon we can get back to doing these in person and provide you with some drinks and pizza. But until then, we'll continue to look to run these events online. Anyone that knows us well will know we run multiple events. So if you go to the roundabouts.co.uk, our series of meetups are on there and what's coming up. Agile Roundabout is our flagship one, and that's the one we're running the most during lockdown. but we are looking to put more on in the coming months. So keep an eye on that. But yeah, I want to thank not just the two speakers, but obviously some of the people at Ocado Technology who have helped set this up. There's quite a few, and they've been really helpful and great to work with. So thank you to them and Ocado Technology. And thank you to Beth, who works with me at TRG, who works hard setting up these events. Like I said, keep an eye on the roundabouts.co.uk. And like I mentioned, if you do put anything online, whether that's LinkedIn, Twitter, if you can hashtag JVM Roundabout, that helps us a lot. But I guess I'll see you all next time. We will be running one in December, it looks like, with a company called Intuit. I'm just getting the last details on that one. And yeah, thanks a lot, everyone.
Thank you, guys.
Thank you.
Yeah, cheers.
Thanks.